fired out of the submarine have pointy tips. However, why is it that modern submarines have rounded tips? What changed after World War II, where submarines would have sharp edges and sharp noses? However, we also note that they used to surface often and run off of diesel and not nuclear-powered power plants. So we're going to investigate why this change Furthermore, occurred. The properties of water are given as such, as well as our parameters for this submersible. Now, Reynolds numbers will fall into three regimes: laminar, transitional, as well as turbulent flow. In this case, when we do the calculation along the length of the submersible, we find out that the fluid flow is actually turbulent. That being said, we know it's turbulent flow, and here is a diagram of the fluid flow about the submersible.
Hello, my name is Justin Chey, and I will be reading for the technical portion of our project. I do, however, hate the sound of my own voice, so for today I will be borrowing the voice of Ryan Gosling. Of a small projectile through water while varying the shape of the projectile face. We hoped to find that the minimum drag would be achieved by a shape in between a perfect hemisphere and a straight cone, rather than a long cone, counter to your intuition. We initially intended to conduct the experiment in 3D, however, we learned that this would be extremely unconventional. Cone profile, a hemisphere shape, and a flat face for comparison. This is an image of these three lines overlaid in MATLAB and adjusted to intersect where the body of the projectile would begin. If you look closely at the curves, you can see that these lines have a very low resolution, which we made adjustable. This demo has 9 vertical points for its resolution, while our final curves had 30. To draw the curves in between these benchmark functions, we coded MATLAB to calculate the rate of change between each line and a number of iterations. Our project utilized 11 iteration frames with 30 points of vertical resolution. Geometry parameters. Because Ansys hates us, maybe, probably, I guess, I don't know, but Ansys was not okay with animating a spline reliably, so we switched to importing these coordinates into Design Modeler. For our domain, we drew a large box around the half profile of our model, with the intake on the left, outlet on the right, and of course the axis at the bottom. The top edge for all of our simulations was given a 0 shear condition, while edges of the projectile were given a 0 slip condition. Our final mesh design featured a much more refined inflation feature, which wrapped around the entire projectile along with an element size bias along the x-axis behind the projectile to get more accurate wakes. Plotting the data gave us this exponential curve that increases as we iterate from sharp cone towards a rounded and then finally the flat edge, which is not what we wanted to happen. Again, we were hoping to see that the long cone was not the optimized solution, yet as far as our tests can show, the pointier the cone, the better. Look, dynamic pressure animate through each frame from flat to pointy, and flat to pointy, and flat, and you get the pointy. What else means? Well, once again, speed turns out not to be the main concern.
Bigger concern is to incorporate sonar technologies for radar purposes, as well as the blunt nose means it can withstand a lot higher pressure. This is because now we don't have to resurface due to nuclear reactors, thus we are underwater and in deep water for a much longer duration, thus the round face is much better.
Although our tests did not prove our hypothesis of slightly curved faces being preferable to reduce drag, we did find results that ended up defending a lot of the engineering decisions that we commonly see in the real world.